Welcome back. In this video, we continue our study of Chapter 4, and we move to Section 4.2 about path connectedness. Path connectedness is a condition which is stronger than connectedness that we defined in the previous section. Okay, so what is the path first? In general, as you may expect, here's the exact definition. If we have a topological space, capital X, and 2 points, small x and small y in capital X, a path joining small x to small y is just a continuous map from a closed interval AB of the real line into the space, such that initially f of A is x and the other endpoint f of B is y. Okay, so here's a picture if you like. So there are two ways actually to think of paths. First way, you can think of a path as being a deformation, a continuous deformation of a straight line segment AB. Okay. So f of A is called f of A and f of B are called the endpoints of the path. Okay. The second way of seeing a path is you can think of a path as a particle moving from one endpoint f of A to another endpoint. The other endpoint f of B as time goes from A to B. Okay. So now we say that the space X is path connected if any 2 points of the space can be joined by a path in the space. Okay, so we'll prove actually that this is stronger than connectedness later. So the first remark is that, as you probably know, the closed interval AB is homomorphic to the standard unit interval 0, 1. Therefore, by a change of variables, we can always assume that the domain of any path is 0, 1. Okay? And this is what we usually do in algebraic topology. Okay. Now, let us give some examples as usual. So, first of all, you may easily check that the intervals of R are not only connected, but they are path connected. Okay. So actually in R, we have equivalence between connected, path connected, and convex. Okay. Okay, because the intervals of R are convex actually. So if you take 2 points in R, we can join them by a straight line segment. So if X and Y belong to an interval, then the whole straight line segment joining X to Y is in the interval, as we observed earlier. Okay. So this is a particular case of. So in R, connectedness, path connectedness, and convexity are the same. Okay, another expected result is that a ball in Rn, equipped with any norm you like, is path connected because it's convex simply. So, and this should be intuitively clear. If you have 2 points in a ball, you can join them by a straight line segment inside the ball. And here's the exact algebraic proof. If you have 2 points x and y in a ball of center A and radius r, we just take what we call the straight line path or straight line segment path, which is 1 minus tx plus ty. When t equals 0, f of 0 is x, and when t equals 1, f of 1 is y. So it's this what we call the straight line path joining x to y. Okay, and now this path is inside the AR. How do you know that algebraically? Geometrically it should be clear actually, but this is the algebraic proof. We replace f of t by its value, and we observe that 1 minus ta plus ta is just a. Okay? So we can factor now by 1 minus t and t. Okay? So we rearrange this. And now we use the triangular inequality. The norm of the sum is less or equal than the sum of the norms. So, and by homogeneity, I can put the scalar outside. So I get 1 minus t, which is positive, times the norm of x minus a. And since x is in BAR, then the distance between x and a is less than r. And since y is in BAR, we get norm of y minus a is less than r strictly. So the sum is strictly less than 1 minus tr plus tr, and this is just r. So f of t is a path in the ball. Okay. So the ball is convex and therefore path connected. Okay, now, as you probably expect, the converse is not true. So a path connected set need not be convex. So One example is what we call the punctured Euclidean space, Rn without 0, for n, of course, bigger than 1, because if n is 1, we just get R star, which is not even connected. Okay, now this should be intuitively clear, because we can always join any 2 points of Rn without 0 by a path, which is not necessarily a straight line segment. Okay, so consider, for example, 2 points x and y in Rn without 0. We may distinguish between 2 points, 2 cases. If x, y, and 0 are on the same line, are not on the same line. So the straight line segment joining x to y is in Rn without 0. So we can join x to y by a direct straight line path. So please draw a figure. Now, if x, y, and 0 are on the same line, we can bypass 0 by choosing a point z not on this line, so it's different from 0. So, and we can go from x to y through z by what we call a broken line path or a polygonal path. Okay, so please draw a figure to understand what I'm saying. Okay. So in both cases, we have a path joining 2 points x and y in Rn without 0. Now, of course, Rn alone is, of course, convex, so it's path connected, of course. Okay, let's trivial example. You should be able to prove that the continuous image of a path connected space under so the image of a path connected space under a continuous map is also path connected. Okay, it's not difficult actually. And so, in particular, if you consider the unit sphere as n-1 in Rn, so this is the n-1 dimensional unit sphere. Okay, it lives in Rn. This unit sphere is path connected, of course, provided n is bigger than 1. Because if n is equal to 1, just get the 2 point set minus 1, 1, and this is not connected. Okay. When n equal to 2, we just get the unit circle as 1. Okay, of course, it's path connected. And if n equal to 3, we get the 2-dimensional sphere as 2. Okay, how do we prove that rigorously? Consider the function g from Rn without 0 into the unit sphere of Rn, which is defined by simply, so g of x is just simply x over the norm of x. Okay, since x is different from 0, we can divide by its norm. Now, this is, of course, continuous. And the image under G of Rn without 0 is precisely the unit sphere, so it's a surjection actually. Okay. Now, since we proved that Rn without 0 is path connected for n bigger than 1, then its image, which is Sn-1, is also path connected, but not convex. Okay. Because here we are talking about the sphere, not the ball. Okay. So this is another example of a path-connected set which is not convex. It's a fundamental example. Okay, now as you expect, a path-connected space is connected according to our definition. Let's prove this rigorously. Suppose that X is path-connected. And by contradiction, as usual, suppose that X is not connected, so it has a separation AB. Okay, so in particular, A and B are not empty, so I choose an element small x in A and an element small y in B. And according to our assumption, there exists a path, F, from a closed interval A. You can take it 0, 1 if you like, joining x to y. Now, AB is connected, okay? And the direct image under a continuous map of a connected space is connected. So therefore, the image of the path is connected. Okay. And by lemma 4.2 of the previous section, this connected set must be either in A or in B, because AB is a separation of the bigger space X. But this is impossible, because f of AB meets both a capital A and capital B. Okay. Therefore, my assumption was wrong. There's no separation of the space capital X. Therefore, capital X is connected. So connectedness is a stronger condition. Now, the converse in general need not be true. And I will give you a fundamental example known as the topologist sine curve. Here's the example. And then I will end the video with a situation where connectedness and path connectedness are equivalent. Okay, the topologist sine curve. Okay, consider first the graph of the function sine 1 over x for x strictly, so x positive and less or equal than 1. Okay, so this is the graph. So S is just actually the curve in green here. Okay, so makes oscillation, smaller and smaller oscillations between -1 and 1 as x tends to 0. Okay, now S itself is connected because it's the direct image of the interval 0, 1 under the map which has two components, x and sine 1 over x. Okay, okay, so S is connected. Therefore, its closure, S bar, is connected as well. Now, S bar is what we call the topologist sine curve. So it actually, what is S bar here? S bar is simply S union the vertical slice joining 0, -1 to 0, 1. So S bar is the figure in green union the figure in red. This is what we call the topologist sine curve. Okay, now why S bar is the union of these two sets? Let us prove this first. Okay, and then I will prove that S bar is not path connected. So S bar is connected but not path connected. Okay, so this should be intuitively clear because we cannot join 0, 0, for example, or any point on the red line here to a point in the green curve. Okay, it's connected because you cannot separate actually the red line from the green line because they are close together as close as you wish together. So it's connected but not path connected because you cannot go from a green point to a red point. This is the intuitive idea behind. Okay, so first, why S bar is the union of these two, of S and the vertical line? Okay, double inclusion. S is always contained in its closure. So we just need to prove that S bar contains the vertical red line segment. How do we prove that? We take an element in the vertical red line. So it's necessary of the form 0u, where u is between -1 and 1. And any number between -1 and 1 is the sign of some element v. Okay? Now, if you consider the following sequence of S, 1 over v plus 2n pi, sine v plus 2n pi. Okay, now sine v plus 2n pi is just sine v, which is u, and 1 over v plus 2n pi as n tends to infinity tends to 0. Okay, so this sequence in S converges to 0, 1, and therefore we know that the limit must be in S bar. Okay, so any element in this red line is necessary in S bar. So we have the first inclusion. Now, conversely, I want to prove that S bar is equal or is contained in S union the red line. So it's enough to prove that any point in S bar not in the red line is necessarily in S, which is the green line, the green curve. Okay, so if xy is a couple, an element in S bar which is not in the vertical line, so it means necessarily that x is positive, x is not 0. Now, I want to prove that y is equal to sine 1 over x. So I want to prove that xy is an S, which means that y is 1 over x, sine 1 over x. So we reason by contradiction. If y is different from sine 1 over x, so we have two distinct elements in R. So we can separate them by two disjoint neighborhoods, v1 and v2, or intervals if you like. Okay, I can draw a figure. Now, I take g of x to be just sine 1 over x. G is continuous, actually. So by definition of continuity, we can find a neighborhood u of x whose image under G is contained in V2, okay, which is the neighborhood of y. Okay, now by definition of the product topology, u times V1 is a neighborhood of xy because it's what we call an open rectangle. And by the separation condition, this neighborhood does not intersect S. And this contradicts proposition 1.8. Okay. Therefore, necessarily y equals sine of 1 over x, which means that xy belongs to S. And that's it. Okay. Now, if you think that this reasoning is a little bit difficult, go back to the figure, which should be clear, actually, that It's like the sequence 1, 1/2, 1/3, etc. What is the closure of the set 1, 1/2, 1, 2, 1 over n to infinity? It's just the set union 0. Okay, so here we have something similar. The closure of the green line is the green line together with the red line. Okay, this is okay. Anyway, now I will prove that S bar is not path connected. I told you why, intuitively, why this is the case. Okay. But here's the rigorous proof. Suppose that there is a path f from a certain interval AC. You can take it 0, 1 if you like, into S bar that joins the origin 0, 0 to a point in the green curve S. Okay, and now consider the set of numbers T in this domain of f AC, whose image under f belongs to the red line. Okay. Okay, so if you think intuitively, if we want to go from 0, 0 to a point in S, at some point we have to leave actually the red line and move to the green line. And this will happen at some time that I will call B actually. So if you consider the set, this is a closed set and it's bounded from above by C. Therefore, it has a supremum. Okay, and this supremum is actually a maximum because the set is closed. Okay, so what does B mean? It's the time actually when, or the last moment where the path, the supposed path, exits the red line and moves to the green line. Okay, this is the meaning of B. Now, if you consider the restriction of f to BC, then this path actually maps B into an element of the vertical slice and maps the other points of BC to points in S. Okay? And since f is a path from an interval AC into R2, then it has two components, okay? Because S bar lives in R2. So let X be the first component and Y be the second component. Since f is continuous, both X and Y are continuous. Okay, now by definition of B, f of B is actually 0 and Y of B. Okay, so X of B is 0 necessarily. And when if T is bigger than B, then we are now in the green curve. So Y of T is sine of 1 over xt. Okay. Now, since X is continuous, it must possess a limit as T tends to B. And this limit should be X of B, which is 0. And therefore, 1 over xt tends to plus infinity. But the sine function has no limit at infinity. Okay. Therefore, Y of T has no limit as T tends to B. T is less than B from the left. However, since Y is continuous, it must possess a limit. So this is a contradiction. Therefore, our original assumption that there is a path joining 0, 0 to an element in S does not exist. Okay, so S bar is not path connected. Okay, now I hope that this is clear enough. But if you want to know why, in a more precise way, why Y of T has no limit as T tends to B, you can reason as follows. Choose an element B prime between B and C. Okay? And consider the image under X, the first component of F, of the closed interval BB prime. X is continuous and this is connected, so the image is connected. It's a connected subset of R, so it's an interval. And it contains 0 because X of B is 0. Okay? So since it's an interval, the interval joining 0 to xb prime is totally contained in the image of bb prime under X. Okay? Now, if n is large enough, 1 over pi over 2 plus n pi tends to 0, so it's close to 0. So it must be in, for n large enough, it must be in this interval 0 xb prime. And therefore, this number actually, 1 over pi plus 2n pi, belongs to x bb prime. So what does it mean? It means that it's in the image of bb prime. So there exists a sequence that I call Tn in bb prime whose image under x is exactly 1 over pi over 2 plus 2n pi. And in this case, y of tn is just sine of 1 over xtn, which is just sine of pi over 2, which is 1. Sine of pi over 2 plus 2n pi, and by periodicity, it's just sine of pi over 2, which is 1. And similarly, if we consider the sequence 1 over pi over 2 plus 2n plus 1 pi, this sequence tends to 0. So if n is large enough, it belongs to 0 xb prime, so it's in xbb prime. So therefore, this sequence is the image under x of a sequence in bb prime. But now, what is y of Sn? It's sine of 1 over x of Sn, which is actually sine of pi over 2 plus 2n plus 1 pi, which is minus 1. Okay, now we have two sequences, Tn and Sn in bb prime. Okay, and bb prime is compact. Therefore, Tn and Sn have convergent subsequences. Now, as usual, as in mathematical practice, in order to avoid subscripts, we may assume that Tn converges actually to some t, and Sn converges to some s. Okay, so we may still denote the subsequences by the same symbol. Okay, this changes nothing actually. So Tn now converges to a point t in bb prime. Therefore, since x is continuous, xtn converges to x of t, and x of t must be 0 actually, because x of tn tends to 0. So, and similarly, x of Sn converges to x of Sn 0. Therefore, by uniqueness of limits, x of s equals 0. Okay, and therefore we must conclude that t is equal to s equal to b, because otherwise x of t will be strictly positive, or x of s will be strictly positive. Okay, because if t is bigger than b, as you observed, x of t is strictly positive because we are on the green line. So we have two sequences, Tn and Sn, that converge to b, because t equal s equal b, but their images under y converge to distinct limits. Okay, so this proves that y has no limit as t tends to b. Okay. Don't worry if you didn't understand everything, but if you understood the idea intuitively, then it's fine. Okay, but I made this remark for the most meticulous students among you. Okay, now let me end by an example where connectedness and path connectedness are equivalent. Okay, so as we said, a polygonal path, as we expect, or a broken line path in Rn is just what we call a juxtaposition or composition of straight line path. Just straight line segment followed by a straight line segment with the same endpoint, and so on. So here's the result. If U is an open subset of Rn, then the following conditions are equivalent. U is connected, U is path connected, so any 2 points can be joined by a path, and 3, any 2 points of U can be joined by a polygonal path or by a broken line. Okay. Now, of course, a path is a particular case of a polygonal path. So 3 implies 2, and as we know, 2 implies 1. So I just need to prove that 1 implies true in this case where U is open now. So this was not the case with the topologist sine curve. So to prove that 1 implies 3, we use what we call a connectedness argument, a very important argument in analysis. So we start by fixing a point x0 in U, and we consider the set capital A of points in U that can be joined to this base point by a polygonal path. Okay. Then we prove that A is not empty, open in U, and closed in U. And now connectedness of U tells me that necessarily capital A is equal to U. Okay. And what does it mean that capital A is equal to U? It means that any point in U can be joined to x0 by a polygonal path. But since x0, this is just x0, since x0 is arbitrary, this means that any 2 points of U can be joined by a polygonal path. Okay. So let us explain this program in details. So first of all, A is not empty because x0 belongs to A, because x0 can be joined to itself by what we call the constant path. Okay, the constant path f of t equal x0. Now, why A is open? Okay, so prove that there is a ball So for every x in A, there is a ball of center x contained in A. Since U is open and x is in A, so x is in U, we have a ball of center x and radius r contained in U, like as in the picture here. Ball is light blue. Okay, and this is U. This is x0. So since x is in A, by definition of A, there exists a polygonal path joining x0 to x. Okay. Now, if y is a point in this light blue ball, we can join x and y with a straight line segment because the ball is convex. So how do we go from x0 to y? We go from x0 to x by a polygonal path and then by a straight line segment from x to y. Therefore, y can be joined to x0 by a polygonal path, and therefore y belongs to A. And therefore, the whole light blue ball is contained in A. Therefore, A is open. Now, the same argument that you used in step 2 can be reversed. So we proved that the complement of A in U is open. Okay, so take a point in the complement of A. Then by definition, x cannot be joined to x0 by a polygonal path. Now, since U is open, we can find a ball of another radius delta. So same thing in light blue, contained in U. Okay. Now, if some point of this light blue ball can be joined to x0 by a polygonal path, then by composition of paths, we can join x0 to x. But x cannot be joined to x0 by a polygonal path. Therefore, no point in the ball bx delta can be joined to x0 with a polygonal path. And therefore, bx delta is contained in U without A. And therefore, U without A is open. Therefore, A is closed. And that's it. So this concludes section 4.2 and the video. Thank you for your attention and see you next time.